In this video, we're going to work a few problems, optimization problems, for functions of several variables. So, before we do a specific problem, let's review the strategy. We want to find local extrema, so if we have a function of two variables, you compute the partial derivatives. And you either see where they don't exist, or you set them equal to zero. That's going to give us two equations and two unknowns, and then we have to do some algebra. Sometimes the algebra is easy, sometimes it's hard. It's algebra. And then, that'll tell us what the critical points are, and then we use the second derivative test to say which ones are maxima, which ones are local minima, which ones are saddle points. Okay, so let's look at our first problem. Our first problem is to find and classify the critical points of this function, the function x minus y times 1 minus xy, and if you multiply it all out, that's x minus y minus x squared y plus xy squared. Okay. So computing the partial derivatives, well, the derivative with respect to x, derivative of x is 1, derivative of y is 0, derivative of x squared y is 2xy, derivative of xy squared is y squared, and that has to be 0. Derivative with respect to y, 0, negative 1, minus x squared, plus 2xy, and that has to be 0. And now we have to go about solving these equations. So, if you take the sum of the two equations, you get that these cancel, and these cancel, and you get y squared minus x squared equals 0. So that means that y is either x or minus x. So let's see which ones work. So first we're going to check things where y equals x, and then we're going to check things where y is minus x. So if y equals x, then we want 1 minus 2x squared plus x squared to be 0. So that means 1 minus x squared is 0. I've just replaced a y with an x. And that means that x is equal to plus or minus 1. So that gives us two critical points. We've got the critical point 1, 1, and we got the critical point minus 1, minus 1. And if you plug them into these equations, you'll see that they both work. Now, the other possibility is if y is equal to minus x. But if y is minus x, then fx becomes 1 plus 2x squared plus x squared. So that's 1 plus 3x squared, and that's never 0. So that doesn't work. Y equals x works, and we found our two critical points. 1, 1, and negative 1, negative 1. Okay, but that doesn't tell us whether it's a maximum, a minimum, or a saddle point. To do that, we have to take second derivatives. So we go ahead and take the derivative of x with respect to x, and that gives us minus 2y, and the derivative of x with respect to y gives us minus 2x plus 2y, and derivative of fy with respect to y gives us 2x. And now we're going to do things separately. Once for the critical point 1, 1, and once for the critical point negative 1, minus 1. When we're at 1, 1, this is negative 2, 0, and 2. And so we want our discriminant, which is AC minus B squared. So that's negative 2 times 2 minus 0 squared is negative 4. And that's negative. So this means it's a saddle point. If you plug in the point negative 1, negative 1, the same thing happens. AC is negative 4, B squared is 0, and you get a saddle point. So the upshot is that we found two critical points, and both are saddles. No local maxima, no local minima, 2 saddles. Okay, for our next problem, we're going to do a word problem. We want to build an aquarium, a rectangular aquarium. We want it to have a volume of 20 cubic feet. And the base is going to be granite, and the sides are going to be glass. And the granite costs more than the glass. And we want to figure out the dimensions that minimize the cost. So we have to define our variables. We let the width be x, and the depth be y, and the height is z. And that means that the area of the base is xy. And the area of the sides are 2xz, that's the front and the back face, plus 2yz, that's the left face and the right face. You put it all together, and you get that the total cost is $5 times the area of the granite area, plus $1 times the glass area. So this is our expression for the total cost. Now the trouble is, that's in a function of x, y, and z. But we have an equation relating x, y, and z. The total volume has to be 20. The volume is x, y, z, so z must be the volume divided by x, y. And in this case, that's 20 divided by xy. So, okay, if we take this value of z and plug it back into our cost function, we get a function 5xy, well, there it is. Okay, and then we can take partial derivatives. The derivative with respect to x is 5y, derivative of this is 0, minus 2v over x squared. So that means that this has to be 0, which means that 5x squared y has got to be equal to 2v. If you take a derivative with respect to y, you get 5x minus 2v over y squared has to be 0. And that means that 5xy squared has to be 2v. Now, if both of these are equal to 2v, that means that x has to be equal to y. Because if x were bigger than y, this would be bigger than this. If y were bigger than x, this would be bigger than this. But they're the same, so x has to be equal to y. Since x is y, we get 5x cubed equals 2v. And in this case, the volume was 20, so that's 40. So x cubed is equal to 8. So x is 2, and y is 2, and z is 5. So that's the dimensions of our best aquarium that will minimize our cost.